I'm responsible for the business development within the EMEA region for virtual manufacturing and costing. What are we doing? We are taking care of manufacturing simulation, like processes like sheet metal forming, additive manufacturing, but not plastics, the metal side. So we have metal in our blood, and that's what my former boss said. And also taking care of bulk forming and the assembly simulation, all about the manufacturing. So talking about how to use the manufacturing simulation as an input to CAE, let me skip the agenda. The motivation and the challenges we have in the simulation. And Audi has presented this slide 4 years ago already, talking about the challenges they have. We have, when we start with the product, we have the press shop, we're producing the parts, we assemble it, then we have the paint shop where we have an oven, and then we have the function and the design. And to reduce the amount of prototypes or to improve the quality of our virtual prototype, there is a need to connect it. Right now, we have on the left side the manufacturing simulation, and then we have the traditional CAE simulations like NVH, like acoustics. We have heard a lot about it today, and it is not connected. We have two completely different groups of people not talking. Everybody is staying in a silo, and there's no connection between. If we want to improve, we have to take into account the manufacturing process. For acoustics, the stiffness was one topic in the presentation. So we know if we are forming a part, there is a reduction of the thickness, we work hardening. We have also residual stresses, and this will all have an impact on downstream simulations. Another aspect, during the development of the product, we have around about 9% of the cost. But during the production, we have to build the tools and we need our material, and this is approximately 2/3 of the total cost of the product. But these costs are defined in the development during the part design. With the part design, we will fix our manufacturing, our material costs, and this is becoming more and more important to take this also into account and to review this. Why is it important to consider these results? 2 examples. Everybody, I think, knows if we have built a part, we test it, we have the distortion in the simulation, and the distortion of the experiment is wrong, is going in the wrong direction, or the seat, there's a crash, it was a back crash, and why is there a difference between experiment and the simulation? I will show these 2 cases later, and if we will take into account the forming, the manufacturing history, we could really improve and get close to the experiment results. Let's talk a little bit about sheet metal forming simulation. We have the engineering process, so we will have a concept, we will design our parts, we will define the manufacturing, the tooling process, and then we have the stamping simulation. So CAE simulation, crash simulation, all starts with the design very early in the process. If you want to take into account the manufacturing simulation, we have the challenge that the data during the design is not available. We don't know how to produce a part. We have no tool geometries, so there's a lack of information of data. What could we do? We need information or simulation results of the manufacturing process in the very early design stage during the design process. And there we have a solution for the sheet metal part. It's a one-step solver, FDI, where we only need part geometry. If we will take a look on the different solver technologies we have available at Hexagon, then we have on the left side the inverse approach. We only need part geometry during the design. This could be the first design, and based on that we could simulate or get a first idea about critical areas within the part. Could we produce it, and we will get first results for the thinning, for the work hardening, for the residual stresses. Later, if we have tools available, we could run incremental simulation or an incremental approach based on shadow elements, or on the right side, the video is not playing anymore, we could also use brick elements and get more detailed results. So starting from the left to the right, we need more data, we need more knowledge about how we produce a part, but we also will increase accuracy of slides for sure. If I'm running with brick elements, a very detailed simulation, I will get even better results of the forming history. But I also have very high calculation times, and as explained before, the data are not available in the very early stage of the design process. Often there have been discussions about the accuracy of the results. Is a one-step approach good enough? Does it really provide good results? Is it correct what we are doing? Or are there some concerns? Should we really run incremental simulation? There have been a research project founded by the German government a few years ago, together with Volkswagen, and they have benchmarked 5 different parts, structural parts with body in white. We had different material grades, different thicknesses, different complexity, and they have compared one-step results with an incremental simulation approach and compared it to the reality. They have measured the parts, they have defined 30 method points, and then they have defined criteria for the error. It's okay if it's less than 5% deviation, and more than 10 is not acceptable. These are the results. Solver A is a one-step solver compared with the incremental, and we could see that overall we have really good results with the one-step. They are close to the incremental in an acceptable way. Only one part 4, there we have some deviation, and it's maybe not okay. If you take a closer look on that, you could see that we need to know and understand how the one-step solver approach is working. Why is it different? We have a part, and in the area here, in the manufacturing process, we have additional material. So I have in these corners a different material flow. Just taking the part geometry, I've shown here an example in the top row. We have a notch, we have not filled, and we could see high thinning values or thickness grains in this area, and it could cause a break. If I'm closing it, everything is okay. So we need to understand a little bit about the manufacturing process, how we could leverage and use it, and not just take the part geometry and run through. So the 2 case studies. This one is from Faurecia, and I think it was at the time where the part was not in plastic, it was still metal. And they have run one step, improved the part design, and have simulated the crash. And I mentioned the difference between the original mesh and with mapped results from the forming simulation. The difference in the lean back of the backrest was 90 millimeter, and this is for a crash a big number, and it's a huge improvement of the accuracy, and we'll decide if they get an approval for the seat or not. Another example is the fork. It's in general an easy part. I'm only showing the results, and the task here was I've shown it at the beginning. They have simulated it, the welding, and it was not okay because we want to place a wheel, we have to place a bolt, and it was not working. Then we have simulated the forming process, 11 stages, I think it has mapped the data and has then simulated the welding, and now we are within the tolerances, just to show the impact. My last slide is talking about the virtual assembly solution. We heard today Hexagon, we have a lot of technologies. We want to connect the virtual world with the real world, with measurement results. To bring all this together, we have to move away from selling a solution and the solution moving forward to workflows. And the virtual assembly solution was presented also in Vegas at Hexagon Live. And the idea here is to exactly connect everything. So we have the smart press shop on the left side, where we have the manufacturing process. We will develop our stamp, check the formability, may do some spring lag compensation, and then we will build our parts. So we will get the first stamp parts, prototype parts, and these will be measured. And now we are morphing the measured results to use it for the virtual assembly simulation. So we have real part geometries and not nominal CAD data. And then we could do the assembly simulation and analyze our gaps. So the workflow, the idea is importing the CAD, doing the stamping simulation. In this case, we want to predict the spring back behavior. We use incremental approach. We could do or want to do the spring back compensation to adjust our tooling. Then we will produce the first prototype parts. We will scan it, compare it. Is the spring back or is the part like the nominal CAD data, or maybe we have to compensate our tools again to improve the spring back behavior. We will morph the scanned data to our quad geometry, and we will also take into account the simulations result, and then we will use this real-world data, this real CAD data, or geometry data, sorry, to simulate the clamping and the welding process. Later, we could use all these informations with EMEA to do quality checks, to do check the quality and to monitor our production. That's what we are actually working on. And this is the end of my presentation. Thank you for the attention.